We spoke already yesterday about what is the reason for delta connections in comparison to star connections. It would be much easier to make the connection of the windings. The reason is that we have, with a delta connection, less harmonics in the currents in the supply network, because the third harmonics is closed here. There's a shortcut for third harmonics. But what we will learn today in the afternoon, the delta connection is dangerous because there's a short circuit loop. Yeah? Short circuit. And we must have a look onto this short circuit loop. Yeah? Now, this is the example PAF 5. You have this example. This is the example with the delta connection, and we will have a look onto the controlling picture, and you see here's the delta connection. Yeah, I have also a special look on the delta connection itself. And this is the delta connection. These are one winding of the transformer, the second and the third winding, and we have 6 tubes, and in one point we must put together these 6 to a 3-phase system. This is at these points, yes? Okay. We say to this construction, this is a parallel system. We also have some constructors use the cross system. The cross system is if the middle phase is a little bit higher than the outside phases. Yeah, this is a cross section. You see also in the example here, a delta connection. What kind of delta connection is this? This is a parallel system. You see this outside conductor is this what we see blue. Yeah? And this is the connection to phase C. Phase A is not seen, and this is the connection to the middle phase B, and there's also an additional reactor in it. Yeah? Okay? Let's have a look in this construction. How can we... this is an electrical board. The delta connection, conductors, and we can use, sometimes you use different arts of conductors in the delta connection, and this is the area 1 and the area 2. Then you can use different conductors in this area and in this area. This is understanding. This is the reason why we have here in this part 2 parts. The second part is not used. There's no conductor. We use always the same conductors in the part 1. And now we would like to understand how this works. You know that we start our absolute coordinate system in this point, and if we have a delta connection, we must go into the negative direction of x-axis, into the negative direction. Therefore, we first, this is important for you if you use this. In the first step, we start here in phase B, we give this value, and in the second step we give this value, and in the third step we give P dry to this value. These are the first steps. And you see, in the first step, if you look into in the middle phase, you see the first step is we go 200 millimeters to the epsilon axis, and the second step we go into the negative direction of x-axis, 1,300 millimeters to the back size, yeah, and then we go down. You see, in the third step, 500 millimeter down. Now this is the construction of the middle phase. You see, this is the first step, the second step, the third step. Yeah, and if we say that there is a symmetrical solution, we have also given this step, this step. In all cases, we can say this is to this axis a symmetrical solution. Yeah? So now we will have a look into the conductor 1 and conductor 3. Well, we will look what is conductor 1. Conductor 1, copper box full plated, 102 millimeters. This is conductor 1, 2 and 3. Here, we must go look here. Conductor 1 is now going 1000 millimeter into the epsilon direction for conductor 1. This may be this, this was the first. Yeah, green. And now we are blue. Go back. And we go back 1500 millimeters, and we go down also 500 millimeters. We have 3 paths given by this and explained in my paper here. We now can see the reactance of the delta connection calculated to the star side, which is about 0.2 milliohms. Not exactly the same, and we have 2 methods of reactance calculation in the star delta coupling, and I will show what I mean with you. I worked with this complex equivalent circuit many years ago. You may have a look on this. This is the delta connection, this is the furnace star connection. You know this. When we think about this, then you have here 1, 2, 3, 4, 5, 6 conductors, 7, 8, 9 conductors, and the total system has an impedance like this, 9 square 9. And if you want to know the current in each of these sections, you must solve this equation. This is not possible. 9 equations of 9 currents, you do not need that. Therefore, in this paper, this is the delta connection, this is the star connection. There is no coupling between the delta and star because these are 0. And this is meaning, if you put this away, then you have no star-delta coupling. No coupling between the delta and the star magnetic fields. And if you make a hook on this, there's a coupling. This method without a hook is my method, and the other method is the method of calculating of Professor Ahlers. He has the equations for all couplings. The couplings are relatively small because the distance is great between the star and the delta connection. But I want to see this big impedance matrix, which is not usable for an engineer. Therefore, we must think how we can make a better solution. The solution is we do not need to calculate 9 currents. We reduce the system of if we have current loops, 3 current loops, A, B, and C, and we make an equation to solving these 3 current loops. And this is what we use for this. And if we have these current loops, we can also calculate the value of the reactances who are given here to the star side. The first, what it is interesting for us will be in our program we have delta star connection. The delta connection is calculated to the star side at the furnace. We call this XA, XB, and XC. This is on the star side. Here are the other reactances of the furnace. And here's the resistance of the furnace. A, R, F. And this part is calculated from the delta side to the star side. Part of the delta connection. Calculated to the star side. We forgot the delta. We do not know how much is the current and the voltages. We must discuss the solution. Okay? And we see that in this example it is XA 0.212 milliohm, A and C, and B is 0.92 for B milliohm. These are these values. Yeah? With the exact solution, and we make settings. Without coupling between these and these, without coupling, you see this is with delta star coupling, and without delta star coupling. We have nearly the same 1.7 and in the middle phase 1.2 milliohms. There are little differences because the coupling, this is far away from the furnace. Okay, this is, you can use this and you see the result of the furnace. I will go back. Settings, put this. The result of the furnace is, the furnace has 2.5 milliohms and the reactance deviation is small. This is nearly a symmetrical system because we have an electrode arm reactor. Yeah? This is, we can make a construction of this, and this is the total system. Okay, this is how to use a delta system. You can also, if you make this long here, you can also, sometimes you do not need this connection. You can check the flexible cables to these points, and then you do not need these two. Yes, and you can connect if there is enough space. You make this long, and you do not need this. Maybe possible, but in this case you can make terrible mistakes, and this I would want to discuss with you. Yeah? Okay. Mistakes may be that some people said, oh, can we make this bigger and give an end to this point. I will show you what I'm meaning. This is example number 6. You have this file. Open. Can we make this? No. This connection for phase B is higher, then you can get easier a triangle position of the flexible cables and of the electrode arm, and therefore people said, oh, can we try to make this construction? I've also made paper of this. I printed a paper of this example. Here, here's my paper. Yeah? We make this higher. And we transform the and say, oh, we make this higher, the impedance of this may be higher, and then can that help to make a symmetrical reactance? Yeah. And many people spoke with me together with, and I have made some researches, and I will speak with you very long what terrible solution they are possible if you make this. this, I say, the nearly delta, nearly symmetrical delta connection, yeah? Nearly symmetrical. This is nearly symmetrical. Okay, this? I will make a new paper and we will try. I do not know the number of this.
Okay, I check this.
You remember from yesterday the last number?
Yeah.
Oh. Well, here we connect A, here we connect C, and here we connect B. And this is the furnace. And I would like to give names A, B, C, A, B, C to this. And the result, we can see the result of this construction there is on this side here, XA is 0.2 milliohms about. XB is higher, 0.4 milliohms about. Yeah, and XC is also 0.2 milliohm. That does not bring much, but we will speak about what are, we see the unsymmetric delta star connection. So, this is on the star side, but we want to look what happens on this side. Therefore, we make a little electrical circuit. Here's point A, here's point B, and here's point C, and we have between A and B here the voltage source UAB, and we have here the voltage source UBC, and we have here the voltage source UCA. Normally, if you have no reactances in the delta, should be the sum of the voltages should be equal. Because this is a short circuit, yeah, it should be the sum UCA plus UAB plus UBC is 0. That means UAB UBC plus UCA is 0, the voltages should be equal and the phase angle is 120 degrees. This 120 degrees, yeah? This is necessary. But there are also impedances in this network. And these impedances come from this unsymmetrical connection. You see, this is on the delta side, on the star side, but they are calculated from the delta side to the star side, and we must calculate it back. You see, here must be a reactance which has the name XAB, and here must be a reactance which is named XBC, and this is a reactance named XCA. And now we have another point. The sum of the voltage drops at this reactance also must be zero. Yeah? We have here a current E from B to A. We have here the current E from A to C. And we have here a current E from C to B, and it should be the sum of the voltage. I will write it down. EBA multiplied with XAB plus EAC XCA plus XECB multiplied with JXBC. This should be also zero. Not the voltages, also voltage drops. Now we would like to know how great are these, which are calculated by the program, but not given out. We are also have a result by this. I can show you how the values are. I've done this very many years before. The values of the system I've prepared some values for you. Yeah. Here they are. These are on this side, and these are special values on the delta side. There are nine. These, and we want to look for the values inside. They are not given by the program, because this is interesting for us. Now, there are some formulas which we can use to calculate from this to this. And I do not have the formulas which can calculate from this to this. I can give you only the results. The results will be, the result is now from XA, XB and XC we calculate XAB, XBC, XCA. XAB is 5x, XBC is 5x, XCA is 5/2x. This means these and these are high values that belong to this big loop, and this little loop from here to here between A and C is small, 5/2x. Now we check if this solution is good or not. We see against these. We first we must think about the currents. We think the system has symmetrical currents. There are 3 equal currents flowing in the system. Symmetrical currents in the furnace. Which means this is I1, this is I2, and this is I3. And if we have a symmetrical system in the star side, the currents in the delta side also must be symmetrical, but they are smaller. Square root of 3 smaller. And you can check the differences between these currents, I1, this current I2, and this current I3, and I find that EAC plus I1 minus this is 0. I don't know. IAC plus this minus this current BA is 0. This is the current law for this point, for the point A. For the point B, we write this current plus this current minus this current is 0. E2 plus EBA minus ECB is 0. And for the point C, the law is E3 plus ECB minus EAC is 0. If we have these outside phases, we can now give the solution of this equation. E1 is EBA minus EAC. E1 is EBA, this must be EBA, yeah. And this must be EAC. E1 is EBA minus EAC. This is this equation. The next equation is for E2 is ECB minus EBA. E2 is minus EBA plus ECB. This is a current in CB. And E3 must be EAC minus ECB. E3 is EAC minus ECB. You see, if you have a symmetrical system in the star side, you must have a symmetrical current flow in the delta side. And you see that the currents in the delta are square root of 3 smaller than the currents in the star side. The transformer windings have a smaller current than in the furnace. Is that clear? Is that clear? Okay. Now we would like, we know now the currents in the delta side, we would like, if this equation is the voltage drops on this unsymmetrical reactance are zero. They are not. Yeah. But we will try this. Now write it down. We make a loop here. And we put these values into this equation, yes? EBA multiplied with JXAB 5x plus EAC multiplied with J5 half x plus ECB multiplied with J5x. Is this zero? No, it is not. Because it would be zero if all x values would be zero. This is not. This is not. This is unlike zero. Not zero. What happens if the sum of voltages in a loop is not zero? There must be other currents. Yeah, there must be more and other currents. The currents are wrong. And this, what happens? What happens? There must be an additional current. We call this Kreisstrom. There is a circle current flowing only as this. I know. And we add this circle current to this. E B A plus E 0 multiplied with J5x plus E A C plus E 0 multiplied with J5 half x plus E C B plus E 0 multiplied with J5x. This must be now 0. Now we can see that we can divide through J. Yes? We can divide also through x, and we, what did I make? We must multiply with 2. Yeah? Then we have 2 times, this is gone, and we have 1, 2, and we have divide through 5, 5, 5, 5. Now we have 2 E B A plus 2 E 0 plus E A C plus E 0 plus 2 E C B plus 2 E 0. This should be 0. And we add here additional ERC and subtrahieren minus ERC. You see that? This is allowed. You see we have 2 EAC plus 2 EBA plus 2 ECB. These are in the sum 0. Then the sum of this is 0. And the result is, we are now ready, ERC 1, 2, 5, 0, and we have a current loop, a loop current which is 20% of the current EAC. It's the same phase. Yeah? There's flowing a loop current, an additional loop current, which is 20% higher than this. You see, in this phase, there's a smaller reactance. It's maybe plausible, and we can change now our diagram here. We have an additional current loop which is added to this loop. This is E0, and the new current in this from A to C, this is the new current E from E and AC. The current is higher, 20% higher. And also we have here ECB plus E0, ECB in this direction. You see, in this phase, CB, the total current is smaller than before, total current, total current, and here also EBA plus E0, this is E0, and this is the total current. So, now we are ready. If you make this construction, then the impedance in this area is getting higher. You see? The impedance now, 5x. And you find up here 5x. 5x. In this part, the impedance in this part here and here is higher, and in this part, the impedance from here to here, the impedance is much smaller, and therefore, in the transformer is flowing in this winding a 20% higher current than calculated, and nobody can see that. You cannot see that. You cannot see that. You can only see that if you make a measurement in this short circuit winding. I also have made calculations many years before. These are in the triangle the currents and the powers and the reactive power and SS, typical power. If there's a total symmetrical system in the star and in the triangle system. If you have this solution, the total reactance together with this is symmetrical. But in the star there's an unsymmetrical system. You can get, especially 25, in this example, 25 higher current, and in the other phases the current is lower. You see that? Lower than 39 kiloamps. And the power is the same, the sum of power, 41 megawatt. You cannot see that, and there's also the reactive power, the same, but the apparent power is different, and this total power of the system, the total appearance is also different. But you cannot see this because in the furnace there's symmetry. And therefore, I would like to see with this lesson, I will talk to you, don't make this. Many people do not know what they make with this unsymmetrical delta construction. What can happen? I've tried to show you, I write there is flowing an additional loop current E0, which is 20% of the rated current in AC. The winding AC can be damaged. Okay, is that clear? This is not so important if you have more reactances on the primary side of the furnace transformer. Then this I know I0 is smaller, but if you have if you have in your system if you have static VAR control on this furnace bus, there's no impedance on this point. Yeah, and if you don't have an additional reactor on the primary, then you can get very much trouble. This is an academic solution, but you should know this, and I want to say, please make a symmetrical triangle construction. Please make this part as short as possible. Short, make this short and try to make a symmetrical system. I have written a few sentences in my instruction manual. You may remember the following principles should be noticed for the design. Delta star conductors on page 35. Delta star conductors have a relatively small reactance. The design of total reactances is going into high reactances. Therefore, delta star connections should be short. Delta star connections with 6 conductors are expensive and should be short. It is possible to construct an additional reactor for reactance symmetry on the delta part. This we did make. The result would be unsymmetrical reactances on the delta part. The voltage drops at the closed loop would not be equal, and there will flow an additional loop current. This current can destroy the secondary winding of the transformer. This I have shown you now. This I like to think about this. If you have special programs for calculating in each part of the system the currents, you will see that, but nobody has that. Only a few people have that. And this is what I want to say to you. Question for this? This is calculated from this to this. Calculated from delta to star. I don't have the equation. I did not find that, but I have the equation to calculate from this to this. This is given by Mr. Ahlers. Mr. Ahlers has given you the equation in his paper. Chapter 6. Yeah, this is a system with 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. 9, square 9 reactances. And he is giving you the equation. Yeah. Yeah. I think this is correct. I will compare it with my paper. It's here. The calculation from this, from delta to star is, we'll try it, XA is XAB multiplied with XCA divided to the sum of these, XAB plus XBC plus XCA. This is this connection. XAB is 5x, XCA 5/2x. And the sum of this is 10, 20, 25/2x. And you see this, and this is gone, and this is gone, and this is gone. XA is X. We call this X. And then we call this 2X. We call this X. And also XB is XBC multiplied with XAB divided to the sum XAB plus XBC plus XCA. This is XBC, 5x multiplied with XAB, 5x divided to 25/2x. You see this is gone. 2x is this. And XC is the same. XCA plus XBC divided to XAB plus XBC. XCA is also X. If you construct these things, this is what I want to say. You can save a lot of money if you don't make this. We should not make this. This is a very important information for you, because many people have thought you can also make this construction from year to year. And this gives you a little bit changing value. It's not necessary, but I tried this, and therefore I said this is an important point for people who make construction of delta star connection. This is also important for people who are constructing transformers. Because if you have a transformer, many transformers make this inside the transformer. And you have sometimes you must sometimes calculate this connection outside the transformer if you have a cheap transformer or an older transformer. I do not know if the transformer companies like this, if you are responsible for this part and they are not responsible. And if there are too much currents in this is not easy to understand. Yeah? Okay. This is this calculation, and this is this calculation. Okay. This I do not have the formula to calculate from this to this. I have searches yesterday in the evening, but I did not find the formula. It was too late for me. Okay? Okay? This is something for your discussion, and you cannot find this in any book. This is a special thing for the people. We have 2:30. Shall we get a coffee?
Okay.
Cup of coffee? Cup. Okay.